Now we consider the set of random variables that are indexed, and each index is an element of some set. Let's call it T. And if this set is one-dimensional and ordered set, then this xt, the set of xt's, is called a random process. Or stochastic process. The difference between random and stochastic is very superficial. They mean the same thing. For some very political reason, some mathematicians, one mathematician chose this term. At that time, that mathematician, Hinching actually, and he was in Soviet Union, and the government didn't like the term random because in communist society everything must be planned, nothing should be random. So this mathematician came up with this term stochastic based on, I think, from Greek term. And if it's more than one dimension, like 2 dimension, 3 dimensions, and so on, then this is called a random field. I think this term random field is more common than stochastic field. I don't hear stochastic field so often. And now, by the way, so let's see some example. If T, this set T is something like, for example, natural numbers, then we have this set at something like x1, x2, x3, and so on. And if this T is more than 2 dimensions, so it's like the Cartesian product of natural numbers, then we have something like x11, x12, x21, and so on. So you should think these random variable as those on grid. So we have number like n and m, and on each grid we have a random variable assigned. So it has something like random variables assigned to each position in space. So this is called random field. Okay. And suppose now we don't talk about random field anymore. It's just a definition. And we only consider random process or stochastic process. Now let's consider the codomain of xt. Codomain. So the set of values which this random variable can take. Suppose this is limited to this finite set of integers. Suppose there are only m possible values for these random variables. So these can be considered as states of this random variable. So for example, if we plot this value of xt, and this varies from 1 to up to m. So random in a random process, each random variable can take one of these discrete values, which are considered as states of this process. Okay. So depending on a random event or random outcome, in one outcome we have this path, in another outcome we have this path, in yet another outcome we have this path. So each outcome is something like this. So omega 1, omega 2, omega 3, and so on. So if one outcome is assigned, we have this function. Okay. Remember, a random variable is actually a function from some set, sample space to real numbers. Okay. So if we assign one outcome from the sample space, then we determine this. Consider this as a function of t. So if we determine one outcome, then the entire curve is determined. And if we choose another outcome from this set, from the sample space, then we determine another outcome, and so on. So from this, we can define a transition. From xn1 to xn2. So if we choose one outcome from the sample space, then we can determine this transition from step n-1 to step n for each n, starting from 1 to possibly infinity. Okay, and if this this series of transitions from 1 to 2, from 3 to 3, and so on, this is called a chain of transitions. And if each transition is if this chain of transitions has the Markov property, and we studied Markov property before, which means the transition from n1 to n, this probability does not depend on the previous states, right? So we can forget about the past. The next step is determined solely by the previous step. I mean, from the present step. Okay, so that's the Markov property in essence. Then this chain is called a Markov chain. Okay, and in particular, if this transition probability, for example, probability that xn takes the value of j, given that xn minus 1 is I, if this probability does not depend on this n or n minus 1, then this is called this Markov chain is called homogeneous. Okay. So what this means is this. Let's consider some example. So let's say this is k minus 1 and k, and suppose we are here. So xk minus 1 is I, and xk is somewhere here, xk is j. So this probability may be different from this probability. Say L minus 1 and L. So same I, and same j. So this transition probability may be different from this transition probability in general. But if they are the same for any values of index, so if it doesn't depend on the index, so this time, then we say this Markov chain is homogeneous. So for a homogeneous Markov chain, we can write like this: Pij, probability that xn is j given that xn minus 1 is I. Note that this Pij depends only on I and j. Okay, and it doesn't contain n, right? So for any values of n, this Pij is the same value, of course. And here we limit our consideration to I and j can take only finite number of values from 1 to n. There are only m states. Okay, so this is called transition probability. Transition probability. Okay. Now, since this is a probability, we have the following properties. For any ij, Pij is non-negative. Of course, it's probability. And of course, this is less than or equal to 1. And also, if we sum over j from 1 to m, because they can take only j can take only m values, Pij, it sums up to 1, right? Because these m values are the only possibilities, and given any condition, if we sum over all possibilities, then it should add up to 1. Okay. Okay, so if Pij is strictly positive, not 0, then we say state I can communicate with state j. Okay, this simply means that transition probability is not 0. Okay. Now, we can summarize all the transition probabilities in terms of a matrix. Let's call this matrix T. So this matrix T is contains its element the transition probabilities Pij. So that is P11, P12, P13, and so on, and P1m, P21, P22, P to 3, P to M, and so on. So this is an M by M matrix. Okay, but remember this property. So if we sum over J means summing over each row, we get 1. Okay, so now if we have any matrix, suppose any matrix Aij, where I and j varies from 1 to m, if each row adds up to 1, then A is said to be a row stochastic matrix. Stochastic. Row stochastic matrix. Okay, as you can imagine, if each column adds up to 1, then we say A is column stochastic matrix. Okay. Now you should solve this exercise. If this is exercise, okay? If A and B are row stochastic, matrices, then AB of course A and B should be compatible so that we can multiply them, then is also a row stochastic matrix. Okay, how do you solve this problem? So since A and B are, let's say, stochastic matrices, let's write elements of A as Aij and elements of B as Bij. Then if we define C as the product of A and B, and its elements are Cij, so by the definition of matrix product, Cij should be this, from K1 to M, and Aik Bkj, right? And since A and B are row stochastic, we have these conditions. Aij is 1 and sum and Bij is 1. Okay, so we have this given. Now what we want to show is that C is a stochastic matrix, row stochastic. So we want to show this summation is 1. So show this. Given these conditions. And the fact that C is a product of A and B. Okay, now consider the absolute probability problem. That is this. J n. So this is the probability that the random process is the random process is at state j after the nth step. Okay, but first of all we need to consider this initial condition. Okay, initially, so before starting the process, we assign this probability distribution for each probabilities for each state. So that is, let's consider it in this way. So from 1 to m, there is a probability that we start from this state 1 or state 2 or state 3 and so on. So this is the initial distribution. Then, given the initial distribution and the transition matrix, what is the distribution of the first step? So how can we obtain this distribution? So that is, so after the first step, what is the probability that we find our path on the state j? Okay, so to calculate this, consider how we can reach here. Okay, so if we are here in position state 1, then we have the transition probability 1j. If we are at state I, then we have the probability that pij, transition probability. But the probability that we are at state 1 is given by this initial distribution, right? And each of the initial states is mutually disjoint, of course. If we are at state 1, we cannot be at state 2, and so on. So they are mutually disjoint. So we can apply the partition theorem. So this one can be written as, if we are at position 1 to begin with, then we can transit from 1 to j. That conditional probability is given by this transition probability, p1j. If we are in state 2 to begin with, then we can transit from 2 to j by this conditional transition probability, and so on. So we can add up all possibilities. So to summarize, we can write like this. I from 1 to m, pi 0, pij. So we have this formula to calculate the absolute probability at state j after the first transition. But look at this. This probability can be considered as a vector, m-dimensional vector, and this is also m-dimensional vector. And this is an m by m matrix. So we can write this in terms of vector matrix product. So let us define this. P n as a row vector. Okay, P1, P2, PM. Okay, so M can be 0 or 1 or 2 and so on. So if we write this in this way, then, and also this is a matrix called T, right? So this equation can be written as this: P1 equal to P0 times T. So this is a vector, this is a vector, and this is a matrix. Okay, now if we continue this argument, then we can calculate this probability. Okay, this should be equal to P1. So second step comes after the first step, so it should be like this: P1 times T. But P1 is this, so this is P0T times T. But this product is associative, so P0 T times T, which is T squared. So now you can guess P3 should be given as this. Matrix T to the power of 3. And in general, we should have this. Okay. Okay, here's one exercise for you. The initial condition here, it should be all these probabilities should be assigned to all the possible states, right? So we should have this relation. So if we add this pi 0 for all possible states, it should add up to 1, right? So given this and the property of the row stochastic matrix, from this relation, can you prove that this summation, so if we add pj1, then does this add up to 1? So try to prove this. It should be, because otherwise the total probability of the first step, if it's not 1, if the total probability is not 1, then there should be something else than the all allowed states. So that shouldn't happen. So that means you should be able to prove this equality. And in fact, in general, you should be able to prove the similar equality for any steps, for any n. So given this formula, can you prove this? How do you prove this? So what we have as facts are, this is a probability distribution that add up to 1, and this is a row stochastic matrix. So that means each row adds up to 1. So using those facts, you should be able to prove these things. Now, based on this expression, let us define this the nth step transition probability, which is written as this: ij, so which is the conditional probability that nth step is at state j, given that the initial state was I. Okay, this is actually the ij element of this matrix. Okay, well, it should be, right? So this looks like, okay, so this is nth power of t, but it is still a matrix. It is still an n by m matrix. So if we take each element of this vector, then it will look like as an partition theorem, application of the partition theorem. And the conditional probabilities are each element of this matrix. Okay. Then from this, you can change this a little bit. P0 times tn minus 1. But this part is P1, right? And tn minus t to the power of n minus 1. And the element of which are Pij to the power of n. So we have this relation. Let's see. Wait a minute. Yes. Okay, so from this to this, we have this, you can see this relation holds. Pijn, which is the element of this, is equal to this k from 1 to m, pik n minus 1, and pkj 1. And of course, this one is equal to pkj itself. So this is the transition matrix itself. So this is merely saying t to the power of n is equal to t to the power of n minus 1 times t. Right? So this t corresponds to this t to the power of n minus 1 corresponds to this, and this corresponds to this. But this has a name. It's called the Chapman-Kolmogorov equation. So this gives the recursive relationship between elementary step to more complex step. Well, anyway, you should see that the problem of a discrete Markov chain is actually reduced to the problem of finding this, the powers of the transition matrix. Once you know this, you can calculate the probability of states at any steps, right? Because we have this. So initial distribution is given. So if we can calculate this matrix, then we can calculate the probability at any step. So how do we do that? Of course, by using computers, it's trivially possible. You can just multiply the same matrix many times and you're done. But let's do it manually for a simple matrix with only two states. Okay. So, and also we often want to find the equilibrium or limiting case where n goes to infinity. Okay. So go, if we apply this transition infinitely many times, does this converges to some equilibrium states distribution, or it doesn't? So that's something we are interested in. Okay. Anyway, let's try two-state case. So when m is 2. So in this case, a transition matrix can be written as this: 1 minus alpha and beta, 1 minus beta, where alpha and beta are between 1 and 0. Because T is assumed to be a transition row stochastic matrix. So if we write in this way, then the sum of each row is trivially 1, right? So 1 minus alpha plus alpha is 1. Beta plus 1 minus beta is 1. So this is a transition matrix for some appropriate values of alpha and beta. Okay. Now, what we want to do is to calculate the power of this matrix for any n. So we want to calculate this. To do so, we first diagonalize this matrix. So if we diagonalize this matrix, it should be written as this: C, D, C inverse, where C is some matrix and D is a diagonal matrix. Okay. And this one is the inverse of C. Inverse matrix of C. Some matrix. So since D is diagonal, it can be written as this: lambda 1, 0, 0, lambda 2. And if you recall linear algebra, then you should be able to find the values of lambda 1 and lambda 2 that are 1 and 1 minus alpha minus beta. So here's an exercise. Find the eigenvalues. So these lambda 1 and lambda 2 are the eigenvalues of this matrix T. Okay. This matrix T is given as this. So if T is alpha, wait a minute, 1 minus alpha, 1 minus alpha, alpha, beta, 1 minus beta, then lambda 1 and lambda, the eigenvalues are 1 and 1 minus alpha minus beta. Okay, and the matrix C, considered as a row vector of column vectors. Okay, so this V1 is a column vector and V2 is a column vector, and these are actually the eigenvectors corresponding to 1 and 1 minus alpha minus beta. Okay, so they are taken as they can be taken as this. If you recall linear algebra, eigenvalues are unique, but eigenvectors may not be unique. Actually, they are usually not unique. They have some degrees of freedom by scaling. So if 1, 1, this vector 1, 1 is an eigenvector corresponding to this eigenvalue 1, then for example 2, 2 is also an eigenvector. So if alpha minus 1 beta is an eigenvector corresponding to this eigenvalue 1 minus alpha minus beta, then any multiple, constant multiple, non-zero multiple of this vector is also an eigenvector. But anyway, we can take this as C. Okay, and then if C is this, its inverse. Now you should be able to calculate the inverse of matrix. This is given as this 1 over alpha plus beta, and beta alpha minus 1, 1. Let's see. This is minus 1. Okay, you should calculate this. These are exercises. So, if we know this eigenvalue decomposition of the matrix T, then we can calculate any powers of T as this. So this is basically T times T times T times T times T, n times, right? N times. So we replace each T with this eigenvalue decomposition. So C, D, C inverse, C, D, C inverse, and so on, n times. Okay, but matrix multiplication is associative, so we can get rid of all these parentheses. Now we have C inverse and C side by side, and since C inverse is of course the inverse matrix of C, so they cancel to become identity matrix. Okay, so this becomes identity matrix, and in this way every C inverse and C in these places becomes identity matrix. But identity matrix multiplied by any matrix is that any matrix, right? So this becomes, after all, D times D times D times C inverse. So this D appears n times. So this becomes C times D to the power of n and C inverse. Okay, so this D to the power of n becomes C times D to the power of n and C inverse. So what's nice about this? What's nice about this is that D is a diagonal matrix. So in this case, this diagonal matrix is this, but whatever the values of the diagonal, let's say lambda 1, 0, 0, lambda 2, this power becomes just the powers of it's a diagonal matrix, but lambda 1 to the power of n and lambda 2 to the power of n. It's still a diagonal matrix. So it's very easy to calculate the powers of a diagonal matrix. Therefore, this T to the power of n is C times, let's see, lambda 1 is 1 and lambda 2 is 1 minus alpha minus beta. So it becomes 1, 0, 0, 1 minus alpha minus beta to the power of n and C inverse. Okay, so this is a lot easier to calculate than this directly. So that's how we calculate the powers of transition matrices. Okay, next let's consider the behavior of this matrix when t goes to infinity. To do so, let's assume that alpha and beta are strictly between 0 and 1. So alpha and beta are strictly between 0 and 1. So it's not exactly 1 or exactly 0, but somewhere in between. So if that's the case, then alpha 1 minus alpha minus beta is between is less than 1, and it should be greater than negative 1, right? Because alpha plus beta is between okay, alpha plus beta is between 0 and 2. So if we subtract negative 1, that is between alpha plus beta minus 1, and if we negate, then we have this. If we multiply everything by negative 1, we have this. Okay, so that means 1 minus alpha minus beta is modulo, its absolute value is less than 1. So if you multiply, if you take the power of n and take n to infinity, then this power will converge to 0, right? And C inverse, they don't involve any n, so they are always constant. So the only term that involves n is this part. 1 to the power of n is just 1, so it stays, and this converges to 0. So that means, after all, t limit n to infinity to the power of n converges to C and 1, 0, 0, 0 C inverse. So substitute the explicit forms of C and C inverse. You should find 1 over alpha plus beta and beta alpha beta alpha. So this is the limiting value of t to the power of n when n goes to infinity. Then if you substitute this into this relation, p0 tn, then try to find this limit. It should be beta over alpha plus beta and alpha over alpha plus beta. Okay, you should prove this. But, we didn't give any specific numbers for P0. So this result means this result does not depend on the initial condition, initial distribution. So whatever the values of P0, so for example, let's say P0 is P and Q, let's say, any constants between 0 and 1. So whatever the values of P and Q, the final result does not involve these values, P and Q. Next, we consider the general m by m matrix. Okay, but the basic idea is the same. So first, we solve we solve the eigenvalue problem to find the eigenvalue and the eigenvectors. So we just find somehow this eigenvalue decomposition. By the way, this is done by solving. First, you need to solve this equation, circular equation, t minus. Oh, wait a minute. First of all, what eigenvalues is this? T and some, let's see, some vector is equal to lambda some vector, right? And we want to find, so this v is a vector, lambda is a scalar. We want to find some non-trivial solution for this equation. And this can be done by this, for example, moving this to the left-hand side and factorizing by v, we have this. So this is a zero vector. Zero vector. Okay, and this I is m by m identity matrix. Okay, for this linear equation to have non-trivial solution, it is required that the determinant of this matrix, t minus lambda I, should be 0. So this will give you some polynomial, mth order polynomial, of lambda. And by the fundamental theorem of algebra, there are m solution for this equation, including redundancy, including degeneracy. So, but since this T has a special structure, that is, it is a row stochastic matrix, so we have this interesting theorem. One of the eigenvalues is always 1, is always an eigenvalue. Eigenvalue. And the corresponding eigenvector is, just this. Everything 1. Is the eigenvector corresponding to this, corresponding to this eigenvalue of 1. We don't prove this, but this is a kind of corollary to a famous theorem of linear algebra called the Perron-Frobenius theorem. So it says something like this. And there are, of course, other m-1 eigenvalues and eigenvectors. But anyway, suppose we have eigenvalues lambda 1, lambda 2, and so on, and lambda m. And of course, lambda 1 is 1, because 1 is always an eigenvector, and we set this as 1. And the corresponding eigenvectors are v1, v2, and Vm, and this V1 is this eigenvector. Okay, and then this matrix C is constructed by arranging these eigenvectors. So each of these vectors is an m-dimensional vector. So this, if you arrange these vectors in this way, this is an m by m matrix. Okay, and the diagonal matrix is of course the diagonal with the eigenvalues, and everything off diagonal are 0. Then we have these eigenvalues and the eigenvectors are the solutions for this lambda I vi, right? So this means we have so this holds for each of I equal to 1 to up to m. So we can summarize all these things in one expression, that is C times V1, V2, V let's see, Vm, and lambda 1 V1, lambda 2 V2, and lambda m Vm. But this is this can be decomposed into this V1, V2, Vm times D. D is this diagonal matrix. So from this expression, this is actually the matrix C. This is C. So we have, oh, wait a minute, not C. This should be, sorry, this is not C. This is T. This is T. Excuse me. So the eigenvector and the eigenvectors and eigenvalues are the solutions for this equation. So from this we have this expression, that is TC is equal to CD. And if we invert C and multiply the inverse of C from the right, we have T equal to CDC inverse. Okay. You should be worried about if this C is actually invertible. Some matrices don't have inverses, so we should be careful if this is really invertible. But it is usually the case, but can we be sure? That's the question. Anyway, so once we get this result, then it's easy to calculate the powers of T. So by the same argument as before, this is C times d to the power of n times C inverse. And calculating the powers of a diagonal matrix is very trivial. So that is just lambda 1 to the power of n, lambda 2 to the power of n, lambda m to the power of n. And that is a diagonal matrix. Okay. Now you should try to solve one example. So suppose the transition matrix is this. That is 1/4, 1/2, and 1/4. 1/2, 1/4, 1/4, and 1/4, 1/4, 1/2. So if you add each row, they are always 1, right? This plus this is 1, and this plus this is 1, this. If you add, it's 1. So if you solve the eigenvalue problem of this matrix, then the eigenvalues are this. Lambda 1 is 1, lambda 2 is 1/4, and lambda 3 is 1/4. And the corresponding eigenvectors are this. So 1, 1, 1, and -1, -1, 2. It can be something else, but it should be multiple of this. V3, 1, -1, 0. So you should check this. So the matrix, the diagonal matrix is the matrix with these diagonal elements, and the C matrix is just array of these three vectors. And you should be able to invert that matrix. And then you can calculate t to the power of n, and if you take the limit, it should become 1/3, 1/3, 1/3, and actually everything is 1/3. So please verify this. Now consider another example where the transition matrix is given by this 1/2, 1/8, 3/8, and 1, 0, 0, 1/4, 1/2, 1/4. In this case, if you solve the eigenvalue problem, then the eigenvalues are 1 and -1 plus 3i. It's a complex number. And here's another complex number, which is the complex conjugate of the second one. And the corresponding eigenvectors are this 1, 1, 1 as usual. And eigenvectors also contain complex numbers. Seven plus 9i, -60 minus 24i, and 26. Maybe you notice that this and these are complex conjugates, and this are complex conjugates, and also this and this are complex conjugates. So we have complex eigenvalues and complex eigenvectors, but still, so this matrix V1, V2, V3, this matrix has complex elements. Nevertheless, this power of t, written as c times d to the power of n and c inverse, this is still a real matrix. Okay, so this is a complex matrix, but this is a real matrix, interestingly. But and otherwise it doesn't make sense. This is a transition this represents transition probabilities. So if that's complex numbers, that means a probability is a complex number, and that doesn't make sense. So it must be real numbers. So therefore, if you take the limit as n goes to infinity, then we should have 8/15, 1/5, 4/15, and actually 8/15, 8/15, 1/4, 1/5, 1/5, 4/15, 4/15. So this should be the result. Anyway, so in some cases, we may have complex eigenvalues and complex eigenvectors, but still, the final results should be all real. Otherwise, it doesn't have any physical meanings. Now let's go back to the gambler's ruin problem and consider this problem as a Markov process. Okay, so let's see. This is number of steps and the amount of stakes of Alice, and she starts with $k, and the game ends when the the amount of dollars becomes 0 or A. Okay, and at each step, let's say at each step, let's say this is ith step, and suppose this is R dollars. And if Alice wins a play with probability P, then the amount of dollar becomes R plus 1. And if Alice loses, so this is I plus 1, uh, with probability 1 minus P, then the amount of dollar becomes R minus 1. Okay. So these are this P and 1 minus P are the transition probabilities. And otherwise, there are no transitions. So the probabilities are all 0. Okay, so this is 0. So that gives us the transition matrix Pij. Maybe I should write P R PRS, and this is P if S is R plus 1, 1 minus P if S is R minus 1, and 0 otherwise. Okay, so the transition matrix becomes something like this. Now, the first element here, one element is 1, and 0, 0, 0, and everything 0. So this is because if Alice has $0, so this first row corresponds to $0, okay, $0, then the game is already finished. So the probability of ruin is 1, and there is no transition to any other states. So the game is over. And the second row, it's 1 minus P and 0 and P. So this first column means the next state. So if Alice has $1, then the probability of going to this state, $0, $1, $1, $2, the probability of transition to this state is P. So Alice wins a play with probability P, and Alice loses a play with probability 1 minus P. In all other states, the transition probabilities are all 0. And if Alice has $2, then this becomes 1 minus P, 0, 0, P, and 0, and 0. So if she has $2, if she loses a play, then in the next step, Alice has $1. And if she wins a play, then Alice has $3, and so on. So at this step, it becomes 1 minus p, 0, p, and 0, 0, 1. So this last row corresponds to the stake of $8. So if Alice has $8 now, then the game is over. So the probability here is 1. The next step is also $8 because the game is over and everything else is 0. Yeah. So this is the transition matrix. Of gambler's ruin problem. And note the structure of this matrix. So it has non-zero elements only around the diagonal. Okay. So in the first row, this diagonal element is 1 and everything else is 0. In the last row, this diagonal element is 1 and everything else is 0. And for every other row, only the elements that are one step off diagonal, those are non-zeros, either 1 minus p or p. Okay, this is called tridiagonal matrix. This form is called tridiagonal because at most 3 elements are non-zeros around the diagonal. Then what is the initial condition? Initial condition is that Alice starts with k dollars, right? So this vector, this row vector, becomes something like this: 0, 0, 0, and 1, and everything else is 0. Only one element is 1. This corresponds to k dollars. Okay, so it starts from 0, 1, 2, and so on, and up to a. So only the kth element, starting from 0, is 1, and everything else is 0. So we could write this thing as this. So each element of this vector is written as delta ij, delta ik. So this is Kronecker's delta. So that means when I and k are equal, then this function is 1, otherwise it is 0. So Kronecker's delta is defined in this way. Is equal to 1 if I is equal to k, 0 otherwise. Okay. Okay, then the next step we want to do is to calculate the power of Tn, the transition matrix. But this is in general very hard to do, so we only consider the limiting case. So by defining Q as the limit of n going to infinity, t to the power of n. So let's try to find the matrix Q defined in this way. Okay. Of course, this is not too easy, but it is reasonable to assume that this Q has this form. I will explain why later. So the first row is 1, 0, 0, and everything is 0. And the second row is U1 and 0, 0. Everything is 0 except for the last column. So, this is a stochastic matrix, row stochastic matrix. So the sum of each row is 1. So if the first element is U1 and everything is 0 except for the last element, then the last element should be 1 minus U1 because this plus this is 1. And similarly, the second row becomes U1 and U2, U3, and up to UA minus 1 and 0, and 0, 0, 0, 1 minus U2, 0, 0, 0, 1 minus U3, and okay, and 0 U minus 1 minus U A minus 1, and the last row is 0 and 1. Okay, why can we assume this form for Q? Okay, that's because this game, Gambler's Ruin Problem, ends when the stake of Alice is either 0 or A, $0 or $8, right? So this Q represents this conditional probability. That is some dollars given given the first stake is let's see, some stake is something. Okay, so when the first stake is $0, then the game is over. So this probability should be 1 when x is equal to 0, and everything else should be probability 0. So this is this. And when this x0 is a, then the game is over, and the end result should be x infinity should be a, because that's the last value of the Alice's stake. So this is 1 and everything else is 0. And for every other possibilities, for example, if x0 is k dollars to start with, then it is the end result is either $0 or $8. Okay, and there are no other possibilities. No, otherwise the game isn't finished. So either let's say this is UK. So either this a K1 element or KA element, okay, 0 element and KA element, they are non-zero and everything should be 0. Okay, so that's why we could assume this form for this matrix Q. Okay, now we note that Q satisfies this equation. Q is equal to QT or TQ. Why? Now, let's look at the definition of Q. Q is defined as this. Right? So this is limit n going to infinity tn minus 1 times t. So this t doesn't involve n, so these could be separated, and this limit, it's still q. So this is q, so it's qt. Or you could write the same thing as tn is t times tn minus 1, and take the limit n going to infinity. Then you have this goes to t, and this t is just t, and this t to the power of n minus 1 becomes q. So that's why we have these equalities. Okay. Now, taking advantage of this, we have 0 tq minus q, which is t minus identity times q. Okay, and this matrix has this form. So just calculate this t minus identity. So that means we subtract 1 from the diagonal elements. Okay, then we have 0 for the first row, and 1 minus p, and minus 1, and p, and 0 for every other elements. And 0, 1 minus p, minus 1, p, and 0, and so on. And times q. So q is something like this. Then simply multiply this matrix with this matrix. Okay, and just do it. The first row is multiplied with the first column of q. So if q is something like this, then that becomes this element. Okay, but this is 0, so everything here is 0, so this is 0. And actually, since the first row is 0, every first row of the resulting matrix is also 0. And same for the last row. These are all zeros. So the last row will be zeros. And the first row is this. These times the first column. So that is, what was it? So this is 1, u1, u2, and 0. So that is u1, 1, u1, u2, and so on. So that is 1 minus p, and minus u1 plus p u2. So this is the 2-1 element of the resulting matrix. And the next 3-1 element becomes 1 minus p u1 minus u2 plus p u3. Okay, you see the pattern? Then we can continue the same procedure for all elements here. But since this Q matrix has non-zero elements only in the first column and the last column, the resulting matrix has non-zero elements only in the first column and the last column. But they are kind of anti-symmetric to each other. And let's look at each non-zero element here. So for example, in this case, we have 1 minus p. Let's pick this one, and u1 minus u2 plus p U3, and these are all 0 because this is zero matrix. And does this look familiar? Maybe we should uh, change the order of terms, so maybe this may look familiar. So in general, it looks like P U I plus 1 minus U I plus 1 minus P U I minus 1. So this is the difference equation we have found in a previous chapter for the gambler's ruin problem. So we got the same result. And solving the gambler's ruin problem means solving this matrix equation. Okay, from now we introduce a bunch of new terminologies. First of all, we consider this transition matrix T, where its elements are Pij. So these indices I and j indicate the states of this Markov process. So this matrix can be considered as a network. It can be considered as defining a network of states. Okay, so there are states. In the case of gambler's ruin, each state represents the amount of dollars Alice has. Okay, so this Pij represents the transition probability from state I to state j. Okay, so Pij. And if this is k, this transition is Pjk, and so on. So some states are connected directly, and some are not connected directly, maybe indirectly, or not at all. So based on this notation, first we define absorbing state. So this is absorbing state. So state I is said to be absorbing. If Pii is 1 and Pij are all 0 for if I is not equal to j. Okay, so this means the diagonal element is 1 and everything else in the same row is 0. So this means if this is state I, then the transition probability from itself, I to I, this is Pii, this is 1. And there are no other transitions possible. So there are no other transitions. Since this probability is 1, this transition cannot go out of I. So in this sense, this state I absorbs the transition. Of course, this is coming out of I, but coming from other states is possible. Coming, for example, from J to I, there can be non-zero transition, but there are no transition out of I to anything else other than I itself. So in this case, this state I is an absorbing state. The next concept is periodic state. Periodic state. First of all, the probability of So starting from I, it can go to some other states and then come back to itself after some time. Okay, so let's say this happens in n steps. Then this probability is written as PII n, which is an element of this matrix, right? So after n transitions, the path that goes out of I comes back to I. Okay. Now, state I is periodic. With period t. So where t is greater than 1. So if PIIN is equal to 0 for n not equal to t or 2t, any multiples of t. And if this is not equal to 0 for multiples of t. Okay, so this means there is non-zero probability of a Markov chain coming back to that state with t steps, or 2t steps, or 3t steps, or multiple of t steps. So in this case, the period is t steps. Okay, and this state is periodic with t with period t. And the opposite of periodic is aperiodic. Okay, so opposite is aperiodic. So this means it's opposite of this. So periodic means this holds for some some integer greater than 1. Okay, then aperiodic means this doesn't hold for any integer greater than 1, any integer t greater than 1. So that is aperiodic. That means this Markov process may come back to the same state after some time, but it's not periodic. So it may come back or it may not come back, but even if it comes back, that number of steps required for the coming back returning is not a multiple of any integers greater than 1. So that's aperiodic. Okay, so let's formalize this a little bit more. So let's define this quantity di, which is greatest common divisor of all integers such that PII n is greater than 0. Okay, so we just run the Markov chain and observe the probability of returning to the same state I after some time. So every time it comes back to the same state, we count the number of steps that was required for this return. Then collect all those numbers and find the greatest common divisor of all these numbers. Then the state I is periodic if this greatest common divisor is greater than 1, and aperiodic if this greatest common divisor is 1. So that means there is no common divisor within all these possible values of n. Now let's see some examples. Let's see. So consider this matrix, this 4 by 4 matrix. 0, 1 half, 0, 1 half, 0, 0, 1, 0, 1, 0, 0, 0, 0, 0, 1, 0. So we can show that all the states here, there are 4 states, and all these states have period 3. They are all periodic states. To see this, we calculate t cubed. Just multiply this matrix 3 times, 2 times, 3 times. Well, anyway, just calculate this, and you should find this is 1, 0, 0, 0, 1, 0, 1 half, 0, 1 half, and 0, 0, 1, 0, 0, 1 half, 0, 1 half. So as you can see, all the diagonal elements are non-zero. So it satisfies at least the necessary condition for periodic states. Now let's define this matrix as S, and you can calculate S squared, which is actually t to the power of 6. But anyway, this is equal to S times S, and you can see that this is actually equal to S. So S squared is equal to S. Okay, any matrix that satisfies this property, when squared, it becomes the same as the original matrix. Such a matrix is called idempotent. Maybe you have learned this in linear algebra, and this also appears in projection matrices. But anyway, so because of this property, any multiple of S, so this becomes S, for example, S cubed is equal to S squared times S, but S squared is equal to S. So this is S squared, but this is equal to S. So any powers of S is equal to S. So that means any power of t to the power of 3 something, let's see, 3r, is equal to S, which is t cubed. Okay. So any powers of multiple of 3 has non-zero diagonal elements. Okay, and on the other hand, if you calculate t 3r plus 1, then it is S times t, and this should become 0, 1 half, 0, 1 half, 0, 0, 1, 0, 1, 0, 0, 0, 0, 0, 1, 0. So these diagonals are all 0. And similarly, if you calculate this, it becomes 0, 0, 1, 1, 1, 0, and 1, 0, 0, 0, 1 half, 0, 1 half, 1, 0, 0, 0. And again, all the diagonal elements are 0. So now this satisfies the sufficient condition for the periodic states. So If the power is multiple of 3, then all the diagonal elements are non-zero. And for any other powers, the diagonals are 0. So according to the definition of the periodic states, then all the states, all the false states here are periodic. The next concept we introduce is the persistent state. Okay, to discuss this, let us introduce this quantity f, j, n. This is the probability that the first return or visit to state j occurs at the nth step. So this n is this n, and the state j is this. Okay, let's try to calculate this quantity. First, consider this problem. Pjj1 is equal to fj1 because if j is visited or returned, the path returns to j for the first time in the first step, then this probability should be equal to this probability, right? Because this is the element of the transition matrix, is the jj element. And similarly, we can write jj n as this. I think we've seen a similar expression before. So this can be written as this. This one, fjr pjj n minus r. When n is greater than or equal to 2. So this means state j is visited in n steps. This probability can be calculated as either the path returns to j for the first time, or maybe for the second time or third time or many times, for the many times. Okay, so it may come back to j multiple times. So this is for the first time, and this part is something like this. So when r is 1, that is fj1 and pjj n minus 1. So that means first this path comes back to j in one step. Then the next n minus 1 step goes somewhere, maybe possibly visiting j multiple times, then come back to j again after n minus 1 steps. So that's the probability. Or it can happen the path visits the state j for the first time in 2 steps. So it visits somewhere else and come back to j in 2 steps. Then after that, it goes somewhere and possibly passing j multiple times and come back to j in n minus 2 steps, and so on. and this happens up to fjn minus 1 and pjj 1. So this path visits j for the first time in n minus 1 steps, and in the next step it comes back to j again. So all these possibilities are summarized in this summation. Okay, now from these equations we can solve for fj. Okay, first from here we have fj1 equal to pjj1, and from this fjn equal to pjjn, oh wait a minute, yeah, pjjn minus this summation, r from 1 to n minus 1, and fjr pjj n minus r. Okay, so this goes like this. First we calculate fj1 from this. This is an element of the transition matrix, so this is given. Then we put n equal to 2, and this is calculated from the square of the transition matrix, so that is, this comes from t squared, and this part comes from t to the power of n minus r. So in principle we can calculate this, and these things r varies from 1 to 1. So if n is 2, this is just, there is only one term, that is fj1, which was obtained from here. Okay, then we can calculate fj3 using fj1 and fj2 in a similar manner. Then we can continue this process indefinitely. Now, using these quantities, let us define this quantity fj without n, that is sum of n from 1 to infinity fjn. So what's the meaning of this quantity fj? This is the probability that the path returns to j after some time, after some steps, or any number of steps. Okay, then state j is said to be persistent if fj is equal to 1. So if the probability of returning to j is 1, then the state j is said to be persistent. Now let's try an example of a persistent state. So consider this transition matrix p1 minus p0 0 0 1 1 minus q 0 q, and of course p and q are between 0 and 1. Okay, in this case q is not 1 minus p, so they're completely independent. Okay, they're completely different values. So to calculate these quantities f1 1 and f1 2 f1 3 and so on, let's consider this diagram. So state 1 2 3, 1, 2, 3. So these vertices corresponds to each state. So state 1, state 2, yeah, state 3. Okay, so from 1 to 1, the transition probability is P. From 1 to 2, transition probability is 1 minus P. And there is no transition from 1 to 3. And from 2 to 3, the transition probability is 1, and there is no other transition. And from 3 to 1, transition probability is 1 minus Q. And 3 to 3, that's Q. Okay, so this F11 is the probability that the path returns to 1, state 1, in one step. So that's P. So this this is the only possibility. Now, the next one, this is ugly. So we consider the probability that the path returns to 1, starting from 1, in 2 steps. And if you consider this diagram, there's no such path. If we go from here, it's already returning to 1 in 1 step, so it's not the case. And if you go to state 2, there's no coming back from state 2 directly. So in 2 steps, there is no way the path can return to 1. So the probability is 0. What about 3 steps? So 1, 2, 3. So that's the probability. So that is 1 minus P times 1 times 1 minus Q. And if you continue this, what about 4 steps? 1, 2, 3, and 4. So after 3 steps, we can calculate any number of steps in this way. 1 minus P, so that's first step, and second step, and third step, fourth step, fifth step, that loops over at state 3. Maybe 0 times, or maybe some more times. So that probability is Q, and that's n minus 3 times 1 minus Q. So that's F1n. So now we calculate F1, which is the sum of all these quantities. F1n. So that's P plus, let's see, n from 0 to infinity, P1 minus P, Q, actually n, 1 minus Q. So this n varies from 0 to infinity. It's exponent of Q. Okay, so, but this 1 minus P and 1 minus Q, they are just constants. So P plus 1 minus P, 1 minus Q. So this summation is 1 of 1 minus Q. It's just a geometric series. So the sum is this, and this will cancel. P plus 1 minus P, which is 1. Therefore, state 1, and this probability F1 is 1. Therefore, the state 1 is persistent. So this is persistent. Which means the path starting from 1 comes back to 1 almost surely. Next, related to the notion of the persistent state, we define the mean recurrence time. Mean recurrence time. Let's call it mu j. So this is the mean time, a mean number of steps that is required for a path to return to state j if the state j is persistent. Okay, so we assume this state j is persistent, then this mu j, the mean recurrence time, is defined as this, n f j n. Okay, that is very reasonable. And if this is infinity, then state j is said to be null. And if this mean recurrence time is finite, then j is non-null. Okay, so in the previous example, let's calculate the mean recurrence time. So that is mean recurrence time of the persistent state 1. Okay, so that is and from 1 to infinity and f1n. So when n is 1, that is p, and when n is 2, that is, the probability was 0, so we just ignore it. And after that, the form of the probability is like this. So n from 3 and n times n minus 3. So somehow you should calculate this summation, and it is possible to find an analytical solution for this, and that is 1 minus p 1 minus q times 3. Oh, sorry, this is ugly. 3 minus 2q over 1 minus q squared. So this will cancel out. After all, that is 3 minus 2p minus 2q plus pq over 1 minus q, which is finite. So therefore, this state 1 in this example is non-null. Next, the opposite of persistent states is transient state. So transient state. Transient means not persistent. So that means that probability fj, which is the probability of returning to j, is less than 1. So that's, if this is the case, this state j is said to be transient. And let's see an example. Okay, so consider this transition matrix: 0, 1/2, 1/4, 1/4, and 1/2, 1/2, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1/2, 1/2. Then in this case, the state 1 is transient. Okay, let's draw the diagram for this Markov chain. So we have 1, 2, 3, 4 states. 1, 2, 3, 4. And 1, 2 is 1/2. And 1, 3 is 1/4. And 1, 4 is 1/4. And 2, 1 is 1/2. And 2, 2 is 1/2. And 3, 3 is 1. And 4, 3 is 1/2. And 4, 4 is 1/2. So we are saying this state 1 is transient. So let's calculate this probability. F1, 1. So there's no loop here. No loop. So it's 0. And F1, 2. So 1, 2. And that's 1/2 times 1/2. 1, 2. So that's 1/2 squared. And 3. So how can this be achieved? 1, 2, and 3. So that's all 1/2. So that will be 1/2 cubed. And since there's a loop, then we can just infinitely loop over state 2 just before returning to state 1. So in general, we have, oh sorry, it's not 3, it's 1. F1 n is 1/2 to the power of n. Therefore, Fj is the sum of all these, and that is, so 1/2 squared cubed, 4, 3, and so on. So that is n from 2 to infinity. And the result is 1/2, which is less than 1. Therefore, if this is F1. So therefore, this state 1 is transient. So what does transient mean? Now, this probability of returning is not 1. So in this case, it's 1/2. So it may or may not return to 1 if we start from 1. It will return to 1 with probability 1/2. So half the cases, it may not return. So that's what transient means. Lastly, we define the notion of ergodic state. Ergodic state, which is defined as persistent and non-null and aperiodic. So if a state is persistent and non-null and aperiodic, then it is said to be ergodic. So this term, English word, ergodic, sounds very strange, and it actually, this concept comes from statistical mechanics. But we are not going into the details here. So you should examine this model. If the transition matrix is given as P 1 minus P 0, 0, 0, 1, 1 minus Q 0, Q, then this state 1 is ergodic. So that is, it is persistent and non-null and aperiodic. Okay, so what does it mean? Persistent means if we start from state 1, it will almost surely come back to state 1. And aperiodic means it will come back with no period, no specified period. And non-null means what was it? It comes back. The mean recurrence time is is finite. Okay, so it will almost surely come back to this state within finite amount of time, but in non-predictable manner. So it's aperiodic, so we cannot predict when it comes back, but it will almost surely comes back, surely come back, and within finite steps. So that's ergodic state. All right, next we consider the classification of chains rather than states. So this is the property of the entire set of states with transitions in between them. So first notion is irreducible chains. Irreducible chain. So one Markov chain is said to be irreducible if for all pairs of states, so I and J are states, any pair of states, there exists an integer such positive, non-zero, or natural number such that Pijn is greater than 0. So if this holds, then this Markov chain is said to be irreducible. So what does it mean? So if we have two states, I and J, they may, if we start from I, this reaching J may not be possible in one step, but if we can reach state J in a finite number of steps for any pair of states, then this whole Markov chain is said to be irreducible. So any state is reachable from any other states within some steps. So that's irreducible. And so let us introduce some related notions. First of all, this is a very general linear algebraic notion. Let's consider a matrix. Matrix A. We say this is positive. So it's a positive matrix if every element is positive. Okay, for all I and J. So if every element of this matrix is positive, then we say the matrix is positive. Okay. And another definition. Then a Markov chain with transition matrix T is regular. It's said to be regular if and only if there is an integer such that t to the power of n is positive. Okay. So by this definition, if a Markov chain is positive, then if a Markov chain is, wait a minute, if a Markov chain is regular, that means for some integer n, t to the power of n is positive, then it should be irreducible by this definition, right? Because there is some n such that every Pij n is positive. So that's the definition of a regular Markov chain. But not the converse may not be true, right? even if a Markov chain is irreducible, it may not be regular, you know, because different pairs ij may be positive, may be connected for different values of n, right? So you should check this with this example. So 1/3, 1/3, 1/3, 0, 0, 1, 1, 0, 0. So this is a regular chain. So if you calculate this, 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 and so on, at some point, every element will be positive for some integer n. Next, we define the notion of closed set. Closed sets. So if we have a Markov chain where we can define some transition properties, transition probabilities, and I don't write everything here. So for a set of states, so not every states, but some subset of states, it's said to be closed. Let's call it this subset C. It is closed if the following two conditions hold. Any state within C can be reached from any other state within C. Can be reached from any other states in C. Okay, so within C, so any states can be so this state can be reached from the other states, every other states, and this state can be reached from any other states, and no state outside C can be reached from any state inside C. So let's say this is a state outside of C, so this state cannot be reached from inside any state inside C. So somehow this set C is isolated from other sets, other states. So this is a closed set. Okay, one very simple example is an absorbing state. Okay, if this is an absorbing state, once the path Markov chain reaches this state, then it cannot get out. So this will just loop over to itself with probability 1. So this one state is a set consisting of only one state, and that is closed. Okay. And the last notion is the ergodic chains. So that is easy. You already know what an ergodic state is. So a Markov chain as a whole is said to be ergodic if all the states are ergodic. And that's it. So that's all for this chapter.